In this video, we'll discuss the design of control valves. Control valves are the most common final control element, or actuator, in a control loop. Many control valves are pneumatically actuated, meaning that they open and close by the action of a pneumatic signal, or an air pressure. That air pressure pushes against a flexible diaphragm, which raises or lowers the valve plug. A spring behind the diaphragm provides a restoring force, in this case to close the valve, while the actuating signal provides the force to open the valve. Because the valve body is closed, you can't see the position of the valve plug, but a valve position indicator will show how far open or closed the valve is. The valve stem goes through what's called packing in the valve body. The packing prevents the process fluid from leaking past the valve stem and also provides friction for the travel of the valve plug. That friction prevents the valve stem from oscillating, but it can also cause the valve to stick, so that small changes in the signal result in no change in the valve plug position. If the valve is sticking, the signal may have to change by a large amount before the valve stem and plug will actually move. To help overcome this, many pneumatically actuated valves have an electronic valve positioner that drives a motor to correct the position of the control valve. This green valve shown here has a valve positioner mounted on it. In an instrument diagram, we'll see control valves represented by something that looks like a bow tie with a hat on it. The bow tie represents the valve body, the stick represents the valve stem, and the hat represents the contraption containing the diaphragm and the spring. The control valve design equation predicts the volume flow rate Q of a fluid through the valve based on some function of the valve position, or the lift, L, and the square root of the pressure drop across the valve. CV here is the valve coefficient, which indicates the size of the valve. CV is a constant for any valve. The function f of L is what we call the valve characteristic, which describes how the flow rate changes as the valve lift or the valve stem position changes. The lift is a number between 0 and 1. There are many types of designs for valve characteristics, but the most common ones are shown here. An equal percentage valve, a linear valve, and a quick opening or square root valve. A linear valve will have an approximately linear change in the flow rate as a function of the lift for constant pressure drop across the valve. Linear valves are not used as commonly in practice as equal percentage valves. Equal percentage valves are designed so that the change in the flow rate with respect to the lift at any point along the curve is approximately proportional to the flow rate. So why would you want a valve that has a nonlinear behavior like this? To understand the control valve design, we have to consider how the control valve will behave when it's installed in a process. Consider a process for which a pump supplies the flow of a process fluid through a heat exchanger and a control valve. The pump provides a constant head pressure of 40 psi, and the pressure drop across the heat exchanger and the control valve depends upon the flow rate. At the design flow rate of 200 gallons per minute, the delta P across the heat exchanger is 30 psi and the delta P across the valve is 10 psi. It would be nice if the flow through the process were to vary linearly with the valve position L. An equal percentage valve can partially compensate for changes in the pressure drop across the valve with changes in Q. To understand how this works, suppose we were to use a linear valve designed to be half open at the design flow rate of 200 gallons per minute. A linear valve has a valve characteristic f of L is equal to L. Now we can ask the question, how does the flow rate vary with the lift? We'll assume that the fluid has a specific gravity of 1. To find out how the flow rate varies with the lift, we first have to find the delta P across the valve as a function of the flow rate. If we assume that the pressure drop across the heat exchanger is proportional to the square of the flow rate, then the delta P across the valve must be 40 psi, the head pressure at the pump, minus the delta P across the heat exchanger. So the delta P across the valve is a quadratic function of the flow rate Q. Next, we'll size the control valve. That is, we'll find the valve coefficient CV. We want the lift to be approximately 0.5 at the design flow rate of 200 gallons per minute. So we can use the valve equation at the design conditions of 200 gallons per minute with a 10 psi pressure drop across the valve to find out that we want a valve with a size of 125. Now if we plug this back into the valve design equation, we can find out how Q, the flow rate, and L are related. This is a very nonlinear relationship between Q and L for what we call a linear valve, and we haven't solved it yet for Q as a function of L. Q as a function of L looks like this crazy mixed power law. We're interested in how the flow rate behaves over the range of L from 0 to 1. So we would want to plot this to see how it behaves. Before we do that, we'll design an equal percentage valve. Let's suppose we choose an equal percentage valve with R equal to 50, sized to be completely open at 110% of the design flow rate. Recall that R is a parameter in the valve characteristic equation for an equal percentage valve. In this example, R is set equal to 40. But for this design, we'll use an R equal to 50. At 110% of the design flow rate, the flow rate is 220 gallons per minute. At this flow rate, the delta P across the valve is 3.7 psi. We can use this to find the valve coefficient, CV, and we find that the size for our valve should be 114. Now again, we plug the CV and our equation for the delta P across the valve into the design equation, and we get a relationship that looks like this, relating Q to L. This is an implicit equation for Q as a function of L that we can solve numerically. This plot from our text compares the installed behavior of our linear valve to 3 different equal percentage valves with different sizes. You might remember when we sized the equal percentage valve, we found that CV should be equal to 114. Well, the valve manufacturer may not sell a valve with a CV equal to 114, so we have to look in the valve manufacturer's catalog and choose some different valves. Here we chose one with a CV of 115, one with 138, and one with a CV of 92 to compare them. None of these provides a linear relationship between L and Q, but the equal percentage valves appear to be more linear over the intermediate values of L than the linear valve. Then why do we call this valve a linear valve? It's called a linear valve because the valve characteristic is a linear function of the lift. Remember, this plot was prepared assuming constant delta P across the valve. But when the valve is installed in a process like this, the delta P across the valve is not a constant function of the flow rate. At higher flow rates, there's a larger pressure drop across the heat exchanger and a smaller pressure drop across the valve because the valve is open. There's less restriction to the flow. At lower flow rates, when the valve is more closed, there's a higher pressure drop across the control valve and a lower pressure drop across other upstream and downstream units. We made another assumption here that the head pressure at the pump is also constant. This also may not be the case. At higher flow rates, the head pressure at the pump is usually lower, and if you deadhead the pump, that is, you close the valve completely so that nothing can flow, you achieve the highest head pressure at the pump. So valve selection should be done considering how the pressure drop across the valve will change at different flow rates. Linear, equal percentage, and quick opening valves are defined differently by different valve manufacturers. These figures are from a different textbook and show that some valve manufacturers offer many types of plug designs that can provide very different valve characteristics. Equal percentage valves are a very common type of valve that are used when the pressure drop across the valve is a small fraction of the total pressure drop across the system. On the other hand, quick opening valves may be used for cases where on-off control is important or where most of the pressure drop in the system is across the valve. Sizing a control valve means choosing both the valve characteristic, that is, how the flow rate should change as a function of the lift, as well as choosing the valve size, or the valve coefficient, CV. In the example shown here, we did this by choosing a constraint. For the linear valve, we said we wanted the valve to be 50% open at the design flow rate. And for the equal percentage valves, we said that we wanted the flow rate to be 110% of the design flow rate when the valve was completely open. In both cases, we sized the valve by constraining a particular flow rate at a particular position of the lift. Usually, you'll want to model the behavior of multiple options for control valves and choose the one that provides the most linear installed behavior over a range of flow rates and lift that will accommodate process needs. Some heuristics for sizing control valves. In most cases, control valves should account for about a quarter to a third of the total pressure drop across the system. If the pressure drop across the control valve is too large, this increases the costs associated with pumping the process fluid. Alternatively, if the pressure drop across the control valve is too small, then the valve is oversized and the range of available flow rates will be limited. A linear valve characteristic is really only useful for a relatively flat pump characteristic and low delta P across the rest of the system. To design an equal percentage valve, first use Rule 1 to determine an approximate delta P across the valve. And then size the valve, that is, find the rated CV using a minimum of at least 100% of the design flow rate with the available pressure drop. And then compute and plot the flow rate versus the lift. If it's not linear near the anticipated operating conditions, then adjust the control valve size or choose a different value for R and repeat. Control valves can be what are called air to open or fail closed, or they can be installed as air to close, that is, fail open. The selection of an air to open or an air to closed valve should be based on the safety in the case of some failure. In a process failure, for example a power outage, you should assume that the signal going to the control valve, whether it's pneumatic or electronic, will go to zero. And so in the failure, the valve will either open completely or close completely. An air to open valve is one that will fail closed when the pneumatic signal goes to zero. An air to close valve is one that will fail open. Control valves can be designed so that the actuating signal will either open the valve when the actuating signal increases, or if you flip this diaphragm upside down, the actuating signal would close the valve when the actuating signal increases. The diagram shown here is an air to open valve. In a failure, we generally want to isolate energy sources. We would want to shut off the flow rate of things like steam heat, or high pressure fluids, or cryogenic liquids. In a failure, we generally want to drain tanks and depressurize vessels. We also want to dilute hazards and return to ambient conditions. So depending on how we want the process to behave in a failure, we will select either an air to open, which is fail closed, or an air to closed, which is fail open valve. Depending on whether we've chosen a valve that fails open or fails closed, we'll want to select a controller that sends a signal that either increases or decreases to open the valve. That behavior is referred to as the controller action, and we'll talk about that in the next video.